Hello again. This is Math 2270 coming to you from the College of DuPage. The title of this lecture is Using a Cramer's Rule Approach to Solving Systems of Differential Equations. As always, please be an attentive learner while watching this video. By way of introduction, we have seen that we can solve systems of differential equations in various ways, including algebraic techniques of substitution and elimination, as long as we're careful to treat operators appropriately. And we also solve them via Laplace transform techniques combined with some algebra. One could naturally ponder whether Cramer's rule also could be applied. The answer is definitely yes, with some caveats of course, and for some this would provide a convenient structure simplifying the calculations. We explore such a notion in this video. And we'll use the concept of determinants as well. So symbolically, if L1, L2, L3, and L4 denote linear differential operators with constant coefficients, then a system of linear differential equations in two variables, x and y, these are functions of t, can be written as L1x plus L2y is equal to g1 of t, and L3x plus L4y equal g2 of t. Now notice we're assuming we're putting the x's over the x's, the y's over the y's, and the functions over the functions on the right-hand side. Now when we eliminated variables, as we would for algebraic equations, this leads to a decoupled system of differential equations, one involving x and one involving y. So we would have L1 operating on L4 minus L2 operating on L3 is going to be what we will have for x, and that would be equal to F1 of t. Now that's after we have operated on g1 of t with those operators. And L1, L4 minus L2, L3 operating on y would be equal to F2, where F2 is these operators operating on G2. And this shows all of that. So formally, these results could be written in determinants similar to those used in Cramer's rule. Now recall in Cramer's rule, solving for x, you have the coefficient determinant is divided into, and you replace the x column with the right-hand side constants. Well, we're doing the same thing here, except you can't divide by this differential operator, but still you can see that structurally we have the same thing going on. And this again is a determinant because you have these differential operators operating that way. And similarly, this is what we have for y. L1, L2, L3, L4, y is, and now we put these constants in the y column, and that's L1 and L3. So you see you have a nice structure with which to go from here. Also notice that this and this is the same, so the homogeneous solutions are going to be the same functions, although the constants might not be the same. Okay, so the left-hand determinant in each equation can be expanded in the usual algebraic sense, with the result then operating on the functions x of t and y of t. However, on the right-hand side, some care should be exercised in expanding it because these are operators. So you must expand those determinants in the sense of differential operators actually operating on the functions g1 and g2. As in Cramer's rule, if this does not equal to 0 in 15, and this is a copy of 15, and this ends up being a differential operator of order n, then you can see that the system, this one, can be uncoupled into two separate x and y nth order differential equations in x and y. The characteristic equations, as I said, and hence the complementary functions of each of these will be the same, although the constants could be different. And speaking of constants, since x and y both contain n constants, There are a total of 2 n constants that appear, but they are related, as we saw in class last time. And the total number of independent constants in the solution of the system then would be n. Now, if it turns out this equals 0, it's a totally different ball game. There might be no solutions, or there might be an infinite number of independent constants. So this is most useful whenever that does not equal 0. We will look at, and it says here, similar results hold for larger systems, and we'll look at a 3x3 example later in this video. It's actually a very powerful and elegant approach. So here's a problem for you to test your skills on. Solve, and it's the first order system of differential equations. X prime is equal to 3x minus y minus 1, and y prime is equal to x plus y plus 4e to the t. So I invite you to perfect your understanding by practicing this. So I'm going to pause, and or you should pause the video and do some work. Let's see how you did. So you're going to reorganize this so you have x's over the x's and y's over the y's, and right-hand side constants over right-hand side constants. So when you do that, we get d minus 3x plus y equal minus 1, and negative x plus, this is d minus 1 y equal 4e to the t. You see these right-hand functions are one over another. The x's are in a column and the y's are in a column. So then we just look at determinants. So we have d minus 3 minus 1, 1, and d minus 1 operating on x is equal to. And now over here I replace the x column with the right-hand side functions, so that's what I have, and then I have this. Similarly for y, notice that the y, it's going to be the same on this side, but on the other side I'm replacing these right-hand side functions in the y column, and so this is our equation that we will have to solve. And notice that the top is going to be an equation in x only, and the bottom one is going to be equation in y only. Okay, you should do this work, but after expanding, you can find that this is the differential equation for x. D minus 2 squared x is 1 minus 4e to the t, and d minus 2 squared y is equal to minus 1 minus 8e to the t. So we work through to find these solutions. Now notice that the complementary solutions here and here, because we have that, we're going to have e to the 2t plus t, e to the 2t in both of them, but the constants are not necessarily the same. We have c1 and c2 here, and c3 and c4 here. We can annihilate these sides and use annihilator techniques to find out the solution here to the non-homogeneous part. And so we find that x is equal to this business and y is equal to this business. Now, if we substitute both x and y into, let's just say, the second equation, that could be this one, you find out that, oh, we don't have any e to the 2t's over here on the right-hand side, and or t e to the 2t's, and so these coefficients have to sum to 0. So what that means is that C4 is the same as C2, so this one is equal to 0, and C3 has to equal C1 minus C4, and also has to equal C1 minus C2, and we get this. So our solutions then, and we have reduced the number of independent coefficients by half, so this is our solution for x, and this is our solution for y. And again, we have now related the constants because originally it was a coupled differential equation. Let's look at a 3x3 example. So given the system, dx plus dz equal t squared, 2x plus the second derivative of y, this is a second order system, is equal to e to the t, and minus 2 dx minus 2y plus d plus 1 z is equal to 0. And here I'm asking you a different question, not a complete solution, although you should be able to do this, but I'm really just asking you, what is the differential equation for the variable y? Often, when I'm teaching, I can ask problems that have you solving part of a system rather than one system. So this is actually very much a kind of question I might ask. So let's see how you do. Let's see how you did. Okay, so with determinants, and again we have to organize this in the right way, but these are the determinants that we have for y. So we have d, 0, d. We have 2d squared, 0, minus 2d, minus 2, and d plus 1. And here we replace the y column with the right-hand side functions. Now, we expand these determinants in much the way we do. We go plus, minus, plus, and we use cofactors, and that's what we're doing here. And it is very instructive if you're planning on using this for you to go through the calculations. But we have d, that's plus d, you cross that out, and this is the 2 by 2 minor, and so you have that plus. Now this one is minus and it's a 0, so we go directly to this one, and I expand that. That is operating on d. And then over here, what happens is I'm using these as differential operators. So d, cross those out. This is the minor that you have, minus, and this is going to be, let's see, and we're doing this, so we have, oh, it's minus 1, and we have that operating on t squared. Okay, so these differential operators are operating on t squared. So you cross out that row and column, and you get 2, 0, minus 2, d plus 1. And then lastly, this is d, and so we're going to have 2 e to the t minus 2d and 0. So anyway, you do those calculations. Again, it's instructive to do those calculations. So you end up with this being the differential equation that you have for y at the end of the calculation. Again, you should be reminded that d is treated as an operator on the right-hand side, but you can do primarily algebra on the left-hand side because of the properties of operators with constant coefficients. In closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now more than ever, take care of yourself and each other. We're all in this together. God bless you all.